Welcome everyone to the working group meeting. Um, I don't know if some of you remember at ROSCON we had this little round table in this Birds of a Feather sessions, and there I met Gray, um, or actually some of us met Gray, and yeah, he has agreed to present us some of his work um, in OpenRMF, like how basically deliberation is done over there. And now we are all very happy to learn more about that. Thank you for being here.
Oh, thank you for inviting me, and thanks for the introduction. You may need to set me as a presenter for me to share my screen. It's currently blocked out for me. I'll also mention. There we go. Yeah. So I'll also mention I'm recently getting over a pretty bad respiratory infection. So if I suddenly start choking up a little bit, don't be alarmed. I'm okay. It's expected. But I think it should be pretty fine. Can everyone see the slide?
Yes, it works.
Okay, great. Then I'll get started. So I'll start with the motivation for why we're doing OpenRMF in the first place. So mobile robots are pretty intelligent these days. It's sometimes surprising to see the kinds of challenges they can deal with. But they're not so great at understanding each other and dealing with each other's presence. So typically the strategy is they see each other as temporary obstacles and either try to reroute or hope that that obstacle gets out of its way eventually. And in a lot of cases where there's a lot of clutter, it ends up being the latter, and that creates problems like deadlocks. But for mobile robots to be more broadly used, like in the daily lives of people, in unstructured environments, they need to be able to deal with each other's existence, or else you can only have like, one robot per room or floor of a building, and that's just not that helpful. And the traditional warehouse methods for controlling traffic flow don't really work if you have an unstructured environment where things might move around. There might be random new obstacles appearing here and there. So the scope of what we're targeting with OpenRMF is tackling these challenges that are preventing mobile robots from being more widely used. So like, how do they coordinate the sharing of space? How do they coordinate sharing infrastructure, which can be automated doors and elevators? And how do they synchronize with other devices? Like if a robot needs to go somewhere and talk to maybe a stationary robot arm that does something to give it a payload, things like that. So how do we just get all these various devices coordinated, working with each other, not causing problems for each other? And for our current efforts, we're targeting a modest scale. So we see potential for things like hospitals and malls, hotels. We even have a pilot program going on in a library that does bookshelf scanning. But we are explicitly not targeting dense warehouse environments for now. We do have plans to reach that scale eventually, but for now, it's not suitable. We're not trying to be suitable for that. And so some assumptions that we make is there may be multiple vendors needed within one facility, because there's no single vendor that offers a robot that can just do everything that needs to be done. For example, if you, I'm going to talk about hospitals a lot because that's where our biggest use cases are right now. So in hospitals, they'll have robots that they want to clean the floors, but they'll also have robots that they want to use for deliveries. Sometimes it's little ad hoc deliveries. Sometimes it's giant scheduled transportation of like a lot of material goods. And these different use cases need to be performed by different robots because of the nature of what needs to be done. And there's no vendor that provides all these different kinds of robots. So we assume we need to be able to work with different vendors in this framework. And because they're coming from different vendors who have different design philosophies or implementations, they don't offer the same inputs, outputs, or capabilities. So we need a framework that can be adapted to whatever it is that any given robot provides. And we need to be able to deal with dynamic environments that have unpredictable elements. And this last one is both a technical concern and also a political concern, which is that centralized command and control is not necessarily an option. Some of these vendors take a lot of pride in the fleet manager that they license to you when you buy their robots, and they want that fleet manager to be the authority for what their robots are doing. And so OpenRMF cannot demand that all robots obey exactly what we want them to do. We can't take a central control stance on this. So given that scope and those assumptions, the general design of OpenRMF is to first of all have a shared traffic schedule. So all the robots are communicating their intended trajectories through some kind of coordinates that someone somewhere in the chain of command needs to make a decision on, like these are the canonical coordinates that all robots must somehow be able to transform their data into. So the individual robots or fleets can each have their own, coordinates they use internally, but they need to be able to transform into some coordinates that all the different fleets are able to understand. And we've designed OpenRMF to negotiate in order to resolve conflicts. So this is a peer-to-peer negotiation process. I'll talk more about it later. It has some similarities to conflict-based search for anyone that's familiar with that. And when it comes to assigning tasks, we auction them off, and I'll talk more about what that means later. And we provide a stable SDK. We provide C++ and Python. Most of the time people use Python, and that's totally fine. The underlying implementation is in C++ currently. And this approach allows us to keep developing new features and capabilities by expanding the APIs of the SDK while maintaining backwards compatibility. We explicitly are not trying to have a stable wire protocol for the time being because we anticipate there are going to be changes to the algorithms, and that means changes to what information is communicated and how it's communicated. So we discourage using some of the direct messages that are being passed around, and instead we want users to just use the SDKs. So there are two places where deliberation happens within RMF. One is the traffic negotiation. If multiple robots want to move through the same space, how do they all get where they need to go without deadlocking with each other? And then task allocation. If multiple robots from different fleets are able to perform the same task request, how do we assign which fleet gets which task in a way that's fair and efficiently utilizes the available resources? So I mentioned before that we have a heterogeneous scope, right? So let's say you have 3 different robots that all have their different specialties. They're all made by different vendors, so they all have different APIs. And you can think of APIs kind of like puzzle pieces, where if the puzzle pieces don't fit together, then you can't connect them. And this means these different robots can't talk to each other. But we need them to be able to cooperate, because hallways can be crowded. If you have a robot, taking up the entire space of an intersection, then and another robot needs to get through there, then you're just kind of stuck. I want to take a moment here and talk about how important elevators are. So the key driving user story that kicked off the RMF project was 6 years ago. The hospitals here in Singapore were already using robots. In fact, they were already using multiple fleets of robots. They have some robots that deliver these giant metal cabinets full of food from the central kitchen to every single ward in the building 3 times a day. It's a massive operation. It's highly scheduled, very rigid, and it's incredible to see these robots just carrying off these giant metal cabinets in a big parade. At the same time, they brought in some other robots that were to deliver medications from the pharmacy to the ward in an ad hoc way. So if a nurse wants some Tylenol, then they can put in a request on a tablet and get some Tylenol delivered to the patient that needs it. And so this was successful. They got both fleets working, but each vendor that came in demanded full control over their own lift lobby. So they need their own elevators that only their robots use, and every new vendor that they brought in made the same demand. And the hospital wanted to add more automation to their operations, but they had already run out of elevators after just introducing 2 robots. So they literally can't bring in any more robots because they've run out of elevators. So this is a major focus for RMF, is like making it possible for different robots from different vendors to all use the same elevator infrastructure. So for traffic scheduling, so dealing with the space problem, imagine you have these 2 robots that each are starting from somewhere and need to get somewhere. And in the middle, there's a risk of a conflict. So the workflow might go something like this. Wally over here will submit its plan to the shared schedule that I mentioned earlier. So Wally will start over here on the left, move into the center, and then move up. Baymax, when Baymax is producing his plan, he'll see that schedule and plan around it. So Baymax will come to this point and wait for Wally to have moved past. And then once Wally is out of the way, Baymax knows that it's safe to continue. But we don't always have such a nice arrangement. So there can be race conditions, there can be prediction errors. You can get into situations where there's a deadlock. For example, if Baymax just happens to start here in the center instead of back here down the hallway, this gives you a completely different situation, because now neither robot can pursue its goal without the other robot somehow getting out of the way. So they'll both submit the plan that they would like to have to the schedule, and then a conflict will be detected automatically by RMF. When the conflict is detected, it triggers a negotiation and tells these robots, or more accurately, tells their fleet adapters to do a negotiation. So the way that works is each robot will propose its own ideal plan that they would like to do if the other robot just didn't exist at all. After that, each robot will respond to the other robot's plan with an accommodating proposal. For example, Baymax sees that okay, if Wally is going to come at me, then I can move down this hallway, wait here, and then go where I want to go. Meanwhile, Baymax simply has to reject, or sorry, Wally has to reject Baymax's proposal entirely, because there's nowhere safe for Wally to go to get out of the way of Baymax's ideal path. So Wally will submit a rejection to Baymax and will provide some information about different places that Wally is able to move to. With that information, Baymax proposes a new plan that would be ideal for itself that accommodates at least one of Wally's possible paths. So in this case, Baymax would be saying, okay, I'll move up here and then wait, and then back down, and then over and down. And that creates an opening for Wally to move all the way down the hallway, wait here, and then go back to where Wally actually wants to go. Now, one of these overall plans is obviously better than the other, so we can calculate a cost and decide that this overall plan up here has the better cost. And we can scale this up to more robots. So if you have 3 robots all in a conflict, then each one will submit its ideal, and then each robot proposes to each other robot's ideal, saying, okay, if you're going to do that, here's what I can do to accommodate that. And then there's one more round of each robot accommodating to each pair, saying, okay, if you two are doing those things, then I'll do this. And once we're at that layer, we can assign a cost to each of these triple plans. And whichever has the lowest cost is the one we go with. Now, typically, we don't need to expand all of these branches, because usually the first leaf that you reach is usually going to be the best plan anyway. And as you're expanding these out, you can, in an A-star kind of way, you can identify, like, okay, if we keep branching this one out, it can never have a better cost than some other one that we already found a solution for. So you can do some pruning here. But in the worst case scenario, you might expand all of these out and then pick the best. Now, we don't expect every robot to give us like full control over their navigation, or even just breadcrumb level control. Some robot fleets are very strict about what they allow their robots to do, or what kind of commands they're willing to accept, especially the older robots, like the robots that carry the meals 3 times a day. They have a very, very strict schedule, and they don't allow any kind of input from the outside. So we still need to deal with the fact that those robots are in the building, and we can essentially treat them as obstacles for the other robots that do allow some level of control. So we end up with these 3 general categories where if a robot offers full control is a little misleading. It's really more like they allow us to give a breadcrumb path for them to follow, like a sparse path. Then we get all these nice advantages where we can reroute robots to get optimal traffic flow. If there's a very complex conflict, then we can anticipate that ahead of time and just get robots out of it. Just leave this whole area, please. But even if we only get like a pause and resume level of control, we can still take advantage of that and tell those robots to stop at an intersection to prevent relatively simple conflicts, or yield to higher priority agents. But even if we don't get any control at all, if we at least can receive information about what a robot, like where a robot is and where it intends to go, then it can be avoided by the others as an obstacle, and it can be displayed on a dashboard, which is another sort of impetus for OpenRMF. Is every new robot that was being introduced to the hospital introduced a new dashboard that needed to be monitored separately. So the people running the operations would have N different dashboards up and need to have eyes on all of them in order to know what's going on in their facility. And that doesn't scale up as you add more and more different robot fleets. As some future work, we want to allow negotiation to take place on board a robot. The ideal vision that I have for this would be if we can write a ROS NavStack plugin that does this negotiation. That aspiration is a bit down our roadmap at the moment, so I don't think I'll be working on it very soon, but that is definitely the dream endpoint for this. Now, besides traffic control, there's also this task auctioning concern. So if you have multiple fleets that can perform the same task request, how do you decide which one gets it? And we do that through a bidding process. So in order to do this bidding in the first place, we need to have unified task descriptions. So a task description is some kind of serializable data structure that can be interpreted into a predictive model, where the inputs of the model are the initial state prediction and some kind of description of the robot. And the output is what is the predicted state after the task is completed. And this predictive model gets provided to a multi-agent task planner that will search for a minimum cost assignment of tasks to robots. But we'll do this per fleet, which I'll explain a bit later. A task description also needs to be able to generate into a runtime, where the runtime is responsible for generating sequences of task phases, not unlike a behavior tree. But right now, we have something much simpler than a behavior tree. A task phase is generated by the runtime, and it monitors the state of the robot and also the state of the different infrastructure, and issues commands such as telling a robot to navigate to a location, issuing a command, say, telling a door to open or summoning an elevator, and this all needs to lead towards the completion of the task. And human operators or external automated systems can request for phases to be skipped or repeated if, let's say, they're monitoring errors that may be happening or monitoring some state information that RMF doesn't have access to, then there's like a degree of control over that. The current scope for all of this is we assume that each task is assigned to just one mobile robot and that individual tasks do not have any dependency on each other. For future versions, we do want to support multi-agent tasks and also support constraints between tasks. And after seeing Thomas's presentation at ROSCON this year, I'm very interested in using Petri nets for that purpose. Now the task descriptions, we're going with JSON, and there's sort of two flavors. There's a simple pre-made type. So you see the category up here is this is a delivery task, and inside the fleet adapter, there's some knowledge that the description of a delivery task contains a pickup field and a drop-off field, and some knowledge that a pickup includes place information and payload information, etc. So common tasks can be given this kind of simple pre-made description schema with a nice minimal set of parameters to fill in. But we also support custom compose tasks. So here the category is compose. and the description is a lot more complicated. You list a sequence of phases, and within each phase you say what the activity is for that phase. You can also give an on-cancel specification. So if the task gets canceled while this activity is happening, then we perform this on-cancel sequence instead. So for example, if this is a delivery and the delivery gets canceled during the drop-off, then this compose task is saying to instead drop off the payload back at the L2 pharmacy, which was the original place that this payload was picked up. And so this type of task can be defined entirely at runtime, as long as you're using building blocks that RMF knows about. And the key thing here is this category description relationship. So for each different category string, there's some schema that's known internally for what the description should look like and how to interpret that. And you can, there's more information about creating custom tasks at this link. So for bidding, each new task request begins a new auction. And in each auction, each fleet adapter, which is what we use to connect the RMF system to an individual fleet, each fleet adapter does a calculation saying, if this task is assigned to my fleet alongside all the other tasks that were already assigned to my fleet, what would be the new overall cost of completing all of my assignments? And tasks that were previously assigned can be rearranged. So internally, the fleet adapter has some idea of like, for all my assigned tasks, here's which robot I expect will execute that task at which time. And that whole schedule can be rearranged when a new task comes in order to get a more efficient flow. So maybe the new task actually becomes the second thing in the queue, even if there are already 10 things in the queue. And maybe some of the other things that were already in the queue get rearranged because now it's more efficient to like do all the tasks in one region of a facility and then move to another region of the facility and do some other tasks. The task will be assigned to whichever fleet gives the whichever fleet's bid would give the overall lowest cost for the whole system. This is not guaranteed to give a global optimum, but it's always very, very close to the global optimum, if not actually the global optimum, because in all of the use cases we've seen, the difference between the outcomes from this approach and what the global optimum would theoretically be, the difference is negligible to the operations. Like the overall uncertainty of the time that tasks actually take to compute is like a bigger factor in the optimality. So future work for this whole task bidding system would be task swapping. So if circumstances change, allow fleets to negotiate task swaps. So like if my fleet has already been assigned the 10 tasks, but one of those tasks takes much longer than expected to actually finish, then I may want to say, hey, other fleets, if you're not doing anything, maybe take some of this load away from me. So making that negotiable. And when we go on to support multi-agent tasks, we'll need a way to have joint bids where two robots that may provide complementary robots that like both need to be involved in a given task should be able to work together to produce the best bid for themselves as a team. So that'll be an interesting problem to solve. As for how assignments are actually assigned cost, the typical way we do it is the length of time from when a task is allowed to begin until the time it's expected to finish. And you can imagine it's the score is in seconds or something. So if you have 4 tasks that are allowed to begin at noon, and we predict each task will take 1 hour, if you assign them all to one robot, you'll get a cost of 36,000. But if you're able to distribute them between 3 robots, then the overall cost would be 18,000 instead. So I'll stop there and open up to any questions that anyone might have.
Yeah, thank you very much. This was really nice. I think I've seen, I don't know, maybe 3 or 4 talks on OpenRMF by now, and this was the only one that answered some of my questions. Although I have some more, but I would like to leave the first question to someone from the audience, if there is a question. I mean, okay. Philip, yeah?
Yeah, thanks for the presentation. I'm Philip from Node Robotics. So we're basically coming more from the warehouse background, which you explicitly said at the beginning you're currently not covering. Just out of curiosity, because we also had a bit of a look into the whole task description and everything related to that. Have you also looked into how basically other standards are doing it, like mass robotics or VDA 5050?
So, right. Okay. So for mass robotics, that's still a work in progress for them, the task descriptions. So they're working on V2 right now, or, well, I actually don't, okay, don't quote me on that because I'm not actually involved. But my understanding is their intention is to be working on a V2 where coming up with how to describe tasks is an explicit goal. So I don't know what the state of that is. For VDA 5050, it's far too low level, right? So VDA 5050 is about the communication between the centralized command system and the individual robots. And so that's giving missions of the nature of like move along this path, you know. But our task descriptions are much higher level and more about they're more semantic, I guess you could say. It describes like what needs to be accomplished overall with actually no information about how to accomplish it. So deciding what paths to follow and everything, that happens at a layer far below the task description. I will say we looked into things like PDDL, which could be interesting, but I think PDDL would be something we maybe use internally and not a user-facing thing, because we want the description of tasks to be as like simple and like, I guess, non-intrusive as possible. So just telling us what you want to see accomplished and then let the system determine how to accomplish it.
Yep, thanks.
But one last thought on that is, so I'm running an interoperability interest group, and this is a topic that I want to bring up there to see if anyone is aware of any existing standards that fit this niche. So yeah, hopefully I'll schedule a session on that at some point, and I would love to get input from anyone that knows some other standards for us to consider.
Maybe related to this, there is this European project that it's called AI Plan for EU, where a bunch of European university came and kind of developed a framework for planning. And I guess, I mean, this is another planning problem that you could address. I personally worked on a bridge for ROS, and maybe that's interesting to look at. I can post in the chat the link if you're interested.
That'd be great. Thank you.
Yeah.
Okay. So I would be interested in, you said that this negotiation of, I would say, coordination of path is similar to CBS. Is there some space discretization, or how do you kind of make sure that the paths don't collide?
Yeah, so it's all trajectory based. So you give a trajectory through space-time with waypoints that include position and velocity and time. I'm actually, so we're working on a next generation of RMF. I'm actually thinking about removing velocity from that piece of information because I've found it creates more problems than it solves to have to do cubic spline interpolation. It makes it much harder to identify where the conflicts will happen when you have multiple cubic splines and trying to figure out where do these hit each other. So I thought I was being very smart when I decided to use cubic splines because it's like, oh, that supports so many different shapes that robots might travel through. But I think after having a few years of experience with it, it was not beneficial. So yeah, so instead, I think we're going to be moving to just position and time information along a trajectory. And so there's no discretization. It's just everyone needs to agree on some coordinate frame to communicate over. And anyone can use their own coordinate frame internally, that's fine. You just need to be able to take your coordinates and transform them to we sometimes call it the canonical coordinates.
Okay. So I think what you are doing is rather PBS, priority-based search, but
it's a bit of both. It's sort of a compromise between the two, yeah.
Mm.
And I'm planning on I'm planning on continuing to develop this approach and then publishing on it at some point, because I do think that, so I've tried using pure CBS, and I find that it's when it's good, it's really good, and then when it struggles a lot.
Yeah.
And yeah.
I mean, it's NP
So
hardware, so
yeah. So I found that doing something like CBS, but with a little bit of shortcutting where you don't care that much about being the global optimum, I think it's a good strategy that I wanna flesh out a bit more and then try to publish on it.
Okay. So and then maybe another question: do you also do for customers evaluations of their? I mean, if you say Singapore wants to add another fleet to a hospital, then I could
Yeah.
imagine that you would have to say at some point, I mean, you can only add this fleet if it really has these capabilities, and you also kind of are allowed to replan and so on, right? I mean,
Yeah,
otherwise you
yeah, yeah.
soon go into deadlocks. If you just stop all vehicles, then at some point all are stopped, and nothing is.
Yeah, that's a great point. And I always, okay, so a little bit of background. So RMF started when OSRC existed, right? The Open Source Robotics Corporation, which was the for-profit subsidiary of the Open Source Robotics Foundation. The foundation still exists. The corporation does not. So I was an employee of OSRC. Now I'm an employee of Intrinsic. Back when we were OSRC, our business model was entirely consulting. And I anticipated that we would play the role you just described, which is even if we're not the system integrator, doing the actual integration work, we may get pulled in to consult on the prospects of bringing in some new platform and what the requirements would be and how the setup might need to change. As Intrinsic, we're not currently doing that kind of consultation work. So that's, I guess, out of scope for us for now. But we are still developing OpenRMF as an open source project. And so my goal right now, as we work on like the next generation, is to develop tools that are good enough for the different system integrators to figure this out for themselves. So set up describe in this tool what you think your setup should look like, and then run lots of tests to see if it actually works out. We do have some simulation already provided out of the box with OpenRMF, but I think it's not at the if you're familiar with the read, evaluate, print loop, philosophy of rapid prototyping, we really don't have a good read, evaluate, print loop right now, because there's a whole process of like you change your configuration, then you generate an SDF world, and then you run that world in Gazebo. So we're working on a new tool that would let you edit and then immediately run, and maybe save a variety of different scenarios that you want to try out, and then like see which scenario gives you the best outcomes. So that's a work in progress.
Yeah, I see. And I mean, I understand that OpenRMF is this kind of like fleet manager of fleets, basically. But I think, at least if you run a demo, then it would also have some interface to actual navigation of robots. I mean, how do you deal with that? Is there an interface currently where you kind of can send nav2-based ROS robots to places?
So for the simulation, we have a very crude pseudo nav stack where we feed in waypoints for it to go to, and the simulated robot just very stupidly drives towards that waypoint without trying to do any kind of sensing or planning or navigating. It just drives at it. It's not the most accurate depiction of like what real robots would do, especially if it's an AMR. Maybe if it's an AGV, it's not too far off, but AMRs would definitely behave differently, and that's not captured in our current simulation. But it's usually good enough. In fact, what we typically find is that the AMRs strictly do better than the simulation, because they're able to like deal with more more stuff, and RMF is designed so that when the AMR does something different than we expected, we can just like update based on that new information and replan if needed, or renegotiate it as necessary.
Okay, yeah, cool. Good. I mean, I'm also out of questions now. So thanks again for the really nice presentation.
Thanks for having me.
Thank you.
If there are no other questions, I don't have any points for the working group right now. We are in our project Convince still working heavily on this, making sense of the behavior tree, coming up with a formalization of the behavior tree, and the next meeting would be in February. I mean the first Monday of the first Monday of January would be it would be January 1st, and therefore I said let's give us like give us one break in the deliberation working group, and this gives me more the chance to I would still hope that we can have some proposal for this standardization of the behavior tree formalism before that. So before the next meeting, which is, I noted it somewhere, it's the 5th of February. So I would hope to have a proposal of the standardization before then, and then I would, if I have this or we have this, then I would send it around in our mailing list, and please ask you to have a look at it before the meeting, and then we could use the February meeting to discuss it. Yeah, but other than that, I can only wish all of you happy holidays, and we meet next year, I would say.
You too.
Thank you so much.
Bye-bye.
Thanks. Thank you, everybody.
Bye.
Bye, guys.
Ciao.
Bye.
Bye.
Ciao.